Okay, so here we are. I posted the start of the homework for next Wednesday. I'll post more this afternoon and possibly a little bit more on Monday. It's really dark over there. Still dark over there. So you're going to need to be able to see what you're writing. Are there switches up there? Can you look and see if there's some switches on the walls by the door? So not that one. Trying to get the lights on over there. Anyway, okay, so you got next major homework due Wednesday. Starting next Friday, what we'll do is we'll be on the every Wednesday homework, but then on Fridays we're gonna have a lecture, some quiz and lecture. Okay, that's good. All right, now let me try this. There we go. Okay, thank you. Remember what you did? Can you remember? Okay. So we'll start having a lecture quiz on Friday, like a 10-minute max quiz, and mostly based on like stuff we do in that Wednesday's class. Okay, we won't have that today, but we'll talk about that next week. We don't even that time between Wednesday and Friday, not thinking about it at all. Lots of stuff is going to fall out of your brain, so we got to be on a regular basis working on this stuff. Okay, so let's pick up where we left last time. And so review. Okay, so review. These are maybe the two most important things of the semester. We'll be using them so much, so we better really make sure we know what this is about. So I want you to take a minute. I want you to identify each function. So what's the first function? Is just identify it, and the second one, and then explain exactly what it does, what it means, and what it does. Right? What are functions about? Functions are about the covariation, how two quantities vary together. You have an independent variable, and you have a dependent variable. So given that values of the independent variable, you get corresponding values of the dependent variable. So that's kind of frames what you're going to talk about when you say explain what it does. Okay? So take a minute, talk to the person next to you, identify each function, explain what each one does. Go. Okay, identify the first function. What is the first function? It's not on your smartphone. It's not on your smartphone. Identify the first function. Exact total accumulation. Okay? Volunteer, who can explain? What does that do? What does that function do? What does it give? Yes, ma'am.
It accumulates from all the changes in t.
Okay.
X equals a or t equals a to whatever x value.
Okay.
And then it also has the initial amount.
And so then what is that total result then? Yeah, exactly right. She said it accumulates values of x starting from a up to x as t, right? So t changes from a to x, accumulates all those changes in f, and then it adds on all the accumulation from before starting at f. And so then what's the result? What does it give all together?
It gives the total accumulation area.
No, not yet. No, not necessarily area. It might be area, but not necessarily. Okay? Total accumulation, right? So it gives the total amount of a quantity, right? When we say total accumulation, we mean there's some quantity we're interested in, and this total accumulation is going to give us the total amount at x, at the current value of x. It gives you all the lump sum of accumulation up to a, and then the integral part accumulates the changes starting from a, so that we get the total amount at the current value of x. All right, what's the second one? What's the second function? Somebody knew. Identify that one. What do we say that was? Yes, sir. Net accumulation, right? And what does this one do or give?
Tells you change from A to X.
The change in our quantity. So whatever this quantity f, right? Whatever that quantity f is, This one gives us how much change in f starting from a up to the current value of x, right? It gives you how much f has changed starting from x equals a to any current value of x. So all semester we're going to be writing functions like this. We're going to be given situations that we need to model mathematically, and we'll be modeling them with these, okay? It's for all kinds of different quantities. The quantity we're working on now is area, okay? But it could be anything. You know, volume, we saw height of the flag. What else we see? Weight of sand, okay? So any quantity can apply to this. So when we're modeling a situation, what is it we're going to need to write f or a sub f, the net accumulation? What is the key thing? If we want to write down a function like this, what's the key thing we're going to need in order to model a situation with a function like this? The rate function, right? This is the whole ball of wax. We need the rate function, okay? If we have the rate function, then we can write exact net accumulation, and we can write exact total accumulation. And again, that was our thing. If we know how fast, from the whole first week, if we know how fast a quantity is changing at every moment, the rate function, how much do we have at every moment? Those are modeling how much we have at every moment, either as change or as total amount, the first one. Okay, so what will we need to write an area accumulation function? That's what we're working on now. So we want to write an accumulation of area. What do we need? Same answer to the previous question, but now I'm talking about a specific quantity, area. I'm going to need rate of change of area, right? Rate of change of area. So and that's what we're working on, figuring out what is the rate of change of area, generally given a function in the graph in the xy plane. We've got this function. What is the rate of change of area? If we know that, then we can model accumulation of area, either as total or net accumulation. Okay, questions on this review? Super important. Okay? So, using integrals for area, we said a couple things last time. We need to determine the rate of change of area. We just said it now. And then we need to investigate the impact on the integral values on intervals where the function values go negative, right? So we've got sometimes functions are positive and they kind of carve out regions above the x-axis, and then sometimes functions go negative and they carve out regions below. So what's the impact of that on our accumulation function? And we'll get to that later today. So we were in the middle of determining the rate of change function for area. So let's keep working with that. So here's what we did last time. So what was our function f? F of x was just the constant function 3, right? It was the constant function 3. And would we come up with the rate of change of this accumulating blue region, right? The area of that accumulating blue region, what did we come up with the rate of change for that? So we said, if x changes by 1, how much does the area change? By 3. If x changed by 2, how much would the area change? 6. If x changed by a half, how much would the area change? 1.5. And so that, and we know that dA equals the rate times dx. Don't have this on. So we said that dA equals mdx, and this is our rate of change for a constant situation, or a constant rate of change. So looking at all those changes in x and the corresponding changes in a, we quickly came up with what was the rate of change. What was the rate of change? 3, right? The multiplier, whatever change in x you have, when you multiply it by 3, you get the corresponding change in area, no matter what change in x we had. And that was exactly our definition for constant rate of change. So we found that the rate of change was 3. Now, this is a rate of change of area, so it's inches squared per inch of width added, right? Change in x, right? So the change in area per change in x would be our units on that. We said, well, that's exactly, that 3 is the same as what? What's that 3 the same as? That rate of change that we came up with as 3 in this situation is just the same as what? the value of the function, right? That's just the value of the function. But we said that would have a different unit, right? That would be like inches or whatever the unit is in the context, right? So the units are different, but it's the same value. So we're gonna, to get this rate of change of area, we're gonna grab just the value of the function and then change its unit to the right unit for rate of change. But it's the same unit. Or sorry, it's the same value. It's the same value. We're just grab the value of the function to be our rate of change of area, and then make the unit. And so yes, the unit cancels out to be the same, right? Inches squared per inch reduces to inch, but we want to keep it inches squared per inch to keep it as a rate unit, okay? So we want to keep it as a rate unit.
How are the units, Professor?
What's that?
How are the units different? Like inches squared per inch?
Because inches is a distance, right? Inches is how far in inches it is from me to you, okay? That's a distance. But when we talk about the rate of change of area, that's how much the area changes per change in this case, width. You see? So that's totally different, right? Those are totally different animals. Like how much area we get for increasing the width so much. Yeah, mathematically they cancel out to be the same, but they mean totally different things. Okay? Good question. All right. So now the question is, we got a changing function, right? The function is not constant. How are we going to find the rate of change of area when the f is not constant? Okay? So let's take a look at that. And so actually we're gonna do it the same way we did it before. We're gonna do the same way we did before when we came to the same question. We can find amount of accumulation easily with constant rate of change, but as soon as the rate starts changing, well, that posed a harder problem. But we're gonna approach this the same way. So here's the situation. Okay, so I got a function f, and I'm accumulating area down to the x-axis. So the question is, how am I going to find the rate of change when the function is changing? It's not constant. How am I going to find the rate of change? So actually, we're going to do it the exact same way we did it before. So why don't you take 30 seconds, talk to the person next to you. What is the way we did it before, and what do you expect? How we're going to do this to figure out what is the rate of change for a changing function? What's the process we're going to use to figure that out? Go. Yeah. So what's going to be what are we going to do? What's the general idea here? Somebody new, volunteer. What do you think? Yeah.
Use tiny rates of change with a step function.
Right. So you said use tiny rates of change with a step function. So watch what this. If I keep going with the video, watch what happens here. If we zoom in on that current value of x at the function, look what we see. So what happens? So for little intervals, what do we have for little intervals with this new graph? Well, so the function is constant, right? The function is constant, just like our 3. We had that function that was just the one we've done so far. It's just 3 the whole way. So now if in a little interval we have a constant function, we can just apply what we've already learned, right? So that's what you should have talked about. So let's keep going here. So now as x increases, we increase through these intervals, right? So we have delta. Well, we'll talk about that in a second. All right, let's zoom in again. Zoom in even farther so we can see what's really going on here. So x is increasing through these intervals for which we're approximating the function with constant values rather than having it continually change. Okay? So a couple questions for you. First question is the value of delta x fixed or varying in this situation, and what is its current value? Okay, so that's going to be your first question. Your next question is the value of dx, is it fixed or varying, and what is its current value? And to make this easier, I changed the x-axis scale so you can see there it's 90, we're in the 90s now, okay? So the x values are in the 90s. Okay, so a couple questions. Is the value of delta x, is that a fixed in this situation or is it varying in this situation? What is its current value? And then is the value of dx, is that fixed or varying? And what is its current value? Go, talk. All right, one more question, one more set of questions. Same thing. Is the rate of change of area, the rate of change of area, the rate of change of the accumulation of area, is that fixed or varying? And what's its current value? The rate of change of area, is it fixed or varying? And what's its current value? So answer that one too. Go. So somebody knew. The value of delta x, first of all, is that fixed or varying? Yes, sir.
Delta x is fixed at 2.
He says it's fixed at 2. What do you think? Yeah, so your answer tells me that you totally get it, but it's probably a little bit more than 2, like 2.1 or 2.2. Do you see that? It's right?
Yeah.
So it's like 91.4 and then like 93.6. So it's like 2.2. So yeah, but your answer told me that you totally understood it. So yeah, delta x is fixed, and the value of delta x here is about 2.2. Okay? Is the value of dx fixed or varying? Somebody else. Yes, sir. Varying. Okay. What's its current value right now?
95.
So
Yeah.
what is 95? No, 95 is something. What's 95?
95 is the current. It's the current value of the current interval. So from what is it, 93.7 to 95
Mm-hmm.
would be so 1.7. No, I'm sorry.
You're good. No, you got it. All right. So he said dx is varying. Yes, dx varies through these delta x intervals, right? As the value of x increases, dx varies. Dx varies from what to what? Dx starts at, in every interval, dx starts at 0 and varies to 2.2. And then when it gets to the next interval, it starts over at 0 again, right? So dx is varying, and its current value is 1.3. You see that it's 1.3 from about, he said, 93.7 to about 95. So the current value of dx that I paused it, right? I've paused it, and so right now it's at 1.3. Okay, but that dx is varying as x increases, right? Dx varies through those intervals from 0 to 2.2, every interval, 0 to 2.2. It takes on all the values in between. Okay, what about the rate of change? Fixed or varying? Yes, sir?
It's varying
Varying, okay. How is it varying?
because you're using those constant intervals. You're using the starting interval, so it's increasing.
Okay, right. So he's saying as you go from one interval to the next, that rate of change changes. So if you said varying and you were thinking of it that way, that's true. But then how is it fixed also? Yeah.
That's for each interval that we pick a constant.
Right. So if I changed x just a little bit right now, that rate of change would stay the same because within an interval, we've got the constant function. So it's both as long as you argue it the right way, right? It's varying from interval to interval, but within each interval, it's fixed, the rate of change. So what is the current rate of change right now? What's the current rate of change? 1.6-ish, right? 1.61 or something, just like around 1.6. Why is that? So why is that the current value? Why? Because the value of the function is the value of the rate of change. We found that before. When you have, now we've got the constant situation, and we've already discovered that when the function is constant, the value of that function is the value of the rate of change, how fast the area is growing. All right, so this is the same process we had before. We took a changing function, and so now by making it into little constant bits, we can get the rate of change of the area for each little interval and make those intervals small enough. And we've got the rate of change of area. So let's just make a sketch here. So if I've got some function like this, this is f, okay? And I've got my a, and I've got my, say, x. And so in our accumulation function, right, t changes from a to x, right? T, so given any current value of x, we think of t accumulating through there. So if this is t right here, say Here's T. So what we're going to do, we're going to take just a really thin slice, right? A really thin slice at T. And we want to know what is the rate of change of area at T. What's the rate of change of area at T? So how would you, everyone, if you're tracking, you should be able to write something that means the rate of change of area at T. So I'm considering T is a really thin slice, right? So it's a really thin, really narrow interval now. So write it down. What you think that is. So how can you express what the rate of change of area of T is? Write that down. This is today's quiz. All right, and then ask the person next to you and see if you got 100 on the quiz. Go, ready? So what should you write down to represent the rate of change of area T? This was our whole goal here. And then if you think you have that correct, then I want you to write down the exact net accumulation function for area. The exact net accumulation function for area. We're ready to write it down now. What's the exact net accumulation function for area? So make sure you have this right first. And then you're going to write the exact net accumulation. Quiz number 2. Exact net. Net accumulation of area, starting from A, right? So the net accumulation starting from A. Okay. Rate of change. What's the rate? Someone in the back. Someone new in the back. What's the rate of change of the area at T? Anyone got it back there? This is the big theme for the last couple days. Back row. Tell me your name in the white and purple stripes. Yeah? Did you come, Ingrid? Did you come up with it? Is it what? MDX. Is the rate is MDX. Okay, so you, sir. Yeah. dy over dx. F of t. That's what you should have wrote. F of t. F of t. This is everything we've been talking about. That the rate of change is the value of the function. The value of the function is the rate of change. Right? And so we saw that with these little intervals here. As x increases, at what rate is it going to increase? Well, it's going to increase at the value of the function in that vicinity, right? The value of the function in that vicinity. Okay? And our net accumulation function then. So now that we have the rate of change, we can write the net accumulation function, right? So what is that? Somebody knew. The net accumulation function. Yes, sir. Integral from a to x. The rate, yep. That's it. If you did f of t and that integral a to x f of t dt, because why? Because that's the rate of change function for area.
Would it be incorrect if you said integral a to x of r sub a of t?
It would not be incorrect, but the whole point is if I'm looking at this function and I'm trying to do net accumulation of area, what is r sub a of t? Right? What do I have? This is what I have. So this is what I have. And so I need to write, from what I have, I need to write what the rate is. So yeah, you're representing the rate correctly, but from what you're given, what is the rate? F. So F is what we know. So that f of t is the same. She asked if you wrote r sub a of t here, that's correct. But then the question is, given what we know, what's that? Given what we know, what is the rate of change? Well, what we know is we have this function. And we've now beaten this dead horse that the rate of change of accumulation of area is the value of the function. We saw it with a constant rate, and now we argued it for taking little intervals and making those constant. Question?
Why is the integral from a to x and not a to t?
Okay, so x is the current value of x, and for every current value of x, we accumulate from a to x using an alternate variable t. So we think of accumulating all the changes in area starting from A to X. So we need a different symbol, T, to do that. But then X, the current value of X changes. So for every current value of X we have to accumulate from A up to X, and we need a new symbol to do that. Because X represents the right side, and then T represents accumulating all the way up to the right side. And then the right side changes. That's our independent variable of our function. Does that help? Yeah, another question.
T represents like the length of the interval?
No, it's an X value. So it's another symbol to mean a value of X. But it's going to take on all the values of X up to the current value of X.
Okay.
So we need a different symbol, but it is still X values. Good question. More, yeah.
So with kind of what she's saying, so if you were to like kind of shade in up to what point that we're accumulating on there.
Oh, sorry. This is A.
not
Sorry.
T, right?
Sorry. This is A of X. If you were confused,
Okay.
you didn't speak up. This is A of X. This is all the accumulation of area up to the right side.
Okay.
How do we do that? By taking values of T from A to X.
So we weren't looking at up until T.
Yeah. So yes. Sorry. That was a mistake. Yeah. If you think something's wrong, don't hesitate to ask. This is A of X.
If it would have been like up until T, how would we?
So then this would have been T, and we needed still a different symbol. Yeah. So if you'd had A of T, then you'd be integral from little a to T of say f of u du, and then u would be all the values from A up to T. Sorry about that. That was confusing. Okay, does that make sense? Is that better? Yes?
So if we were to plug a number in for X,
Uh-huh.
what would T become? You wouldn't plug that same number in for T.
Okay, good. So let's say X is 95.2. Okay? So X is 95.2. Then what are we saying? And say A is, we're going to start accumulating at 90. So A of 95.2 equals the integral from, say, 90 to, this will be now 95.2. Now, do we plug something in for T or not? No, because T has to vary from 90 to 95.2 to accumulate the area. So T is still, it's a value of X that's going to vary from 90 to 95.2 to accumulate all that area. So, this thing, is it a value or is it a function? Now it's a value, right? It's the accumulated change in area starting from 90 and ending at 95.2. And we need that variable T to represent all X values changing from 90 to 95.2. Great discussion. More questions? Good.
So dt is the width of the interval that we're adding.
Super small.
Yeah, and if we're pretending that it's almost infinitesimally
Yeah.
small,
Mm-hmm.
that's why we can add just the value every time.
Yeah, so it goes back to when we had constant, we did dA equals, remember that example? 3 dx. Right? So now it's just that this is super, super small. There's our rate of change. And then multiply together and you get the corresponding little change in area. So this is a corresponding little change in area. And we're accumulating all those little changes in area starting at A and ending at X. Better?
Yeah.
Keep it coming.
Since we've now gotten rid of the X, we can change it with T back to X's or any letter.
In only since we plugged something in. So you're saying,
In that final equation,
Yep.
the integral from 90 to 95.2, that could be F of X.
now you could have those be X's. That's fine. But the problem is, if that's an X and this is an X, that's where you run into problems. But once you actually plug a value into the function, any symbol there is fine. In the function, you can have any symbol as long as it's different than your independent variable. But it is values of the independent variable, but it's got to be a different symbol. More questions? Okay. Okay, so here's a function relative to this situation here. I got capital F of X equals 1 to X, f of t dt. F of X equals 1 to X, f of t dt. So given this situation, in that function, identify that function. What is it? Tell the person next to you. What is that function in this situation? Integral 1 to X, f of t dt. So first and foremost, it's an integral. It's f of x is an integral from 1 to x. So what's that? Always. Net accumulation. Or exact net accumulation. Okay? Of what? In this case, of what? So, what does f of t represent in the integral? Represents rate of change. And we know f of t is the rate of change of what? Area. So now we want, so that's just to see if you recognize it from the other direction, right? So giving you the integral function, do you see that that's exact net accumulation of area? Because f of t, the function value we've shown now is the rate of change of area. So now the question is, what's the impact of the fact that sometimes function values are positive and sometimes they're negative. And so let me give you a visual of function value. So here now I'm showing you an arrow to give you a visual of the current function value, right? So that height away from the x-axis is the current value of the function. So now it's positive, but now it's negative. So what's that going to mean as we're accumulating here? What's that going to mean for the value of capital F, this function capital F? What's it going to mean now? What's going to be happening to the value of capital F now? It's going to be decreasing, right? It's going to be decreasing because values of little f are negative. So it'd be increasing up to 2, but now this capital F function is going to start decreasing. And in the end, do you think the value of f at 3 is going to be positive or negative? Negative, because it looks like there's more decrease in the second half than there is increase in the first half, right? Okay, so in light of that, is capital F an area function? Is it tracking how much area is accumulated? Okay, so the answer is no, because area is always positive. There's no such thing as negative area. Area is always positive. It's always a positive quantity. It's some amount. Right? So capital F relates to area, but it's not area. So what we're going to call capital F is what we call signed area. Signed area can be both positive and negative. And it's the accumulation of what? Areas above the axis where the function is positive, and then it's going to end up subtracting out areas that are below, right? So if you think of that area, the gray as area, then what happens in capital F? That gray area gets subtracted in the final value of capital F. Does it make sense? So anything where F is above is going to have a positive contribution to the signed area F. And anytime the function goes below the x-axis is going to have a negative contribution to the signed area capital F. Does this make sense? So you need to distinguish between area and what we're going to call signed area.
So like if it was area, then we would have added both areas.
What's that?
If it was like...
Yeah, so if we want an area function, if you truly want the area function, not the signed area function, you would be adding the area of the green region plus the area of the gray region if you were at 3. Okay, if you were all the way at 3, you would add the green plus the gray area.
So it would be negative, positive if you were doing an area, a true area function.
So we'll talk about that in a second. So let's just focus on signed area. So we just have the net accumulation of the function, which is our rate of change. That's signed area. And anytime that function goes negative, now it's going to have that current accumulation will have a negative contribution to that function capital F. Is there a question over here? Yes. So f of 3, you guys told me capital F of 3, greater than 0 or less than 0? Predict that it's less than 0, right? So signed area can be positive or negative, depending on which which accumulation won out. Did the accumulation above the axis win out, or is it winning out? The accumulation below the axis, is it winning out? That will determine whether signed area is currently positive or negative. Okay, there was a hand over here. Is it resolved? Good, okay. So questions about this? So before we get to area, we really got to understand signed area. We want to make sure we understand signed area. That's if you just throw the function into an integral and create the net accumulation of the function, then you're going to get signed area, because anytime that function goes below the x-axis, you're going to have negative contribution to the value of capital F. So that's what we're going to call signed area. Yes, please.
So would signed area essentially be the same thing as net area? Like
Yeah, some people call it net area. Okay. Yeah. So, but net area still kind of sounds like it's going to be positive in the end, right? So that's why I want to say signed area. So this function right here is signed area, not area. Now that function, it is area, what? From 1 to 2. As x changes from 1 to 2, it's area, because f is always positive. But as soon as little f becomes negative, it's not area anymore. So in general, that's always we can always say it's signed area. Okay, so now for this situation here, I've got two functions, p and q. So I want you to identify what function p is and what function q is by looking at how the numbers are changing for the current value of x, and then come up with a equation that relates p and q. So what is p and what is q? And can you write an equation or a function that relates p and q? So study what's going on, talk amongst yourselves. I'm going to start taking attendance. Go. What is p? What is q? Write a relationship of the two of them. And talk here. All right, what'd you come up with? What do you think P is? First of all, what do you think P is? It's also what? So yeah, right, it's the rate of change of area, and it's also the value of the function. So P of n, you should have come up with that the value of P is f. And what about Q?
the accumulation from 1 to 2.
Okay, so you should see that it's the signed area that we were talking about, right? It's increasing, still increasing, but what happens now? It starts decreasing, and then what, like we predicted, when you get to the end? Negative. So how do we write a relationship between those two? Volunteer, how could you write, yeah? Q, can I do Q of x? Q of x equals? This is what you should have came up with. That Q of x, that's signed area. So signed area is the integral from 1 to x p of t dt. Okay, I got a new one for you. So questions on that? Do you see that? If you identify p was the value of the function, and that's also the rate of change of signed area. And then q was the signed area. So Q of x equals 1 to x p t dt. Does it make sense? Okay, new one. Now I got a g function and an h function. And I want to see if you can make heads or tails of what g is and what h is. Talk it out. Go. So g, here we go. Ready? I'll write it down. G is signed area, but from 2. So we can go back to p of t or f. You could write p or f, right? Because those are the same. Now, what's h? Did you see what h was? What happens to h now? It does the same thing as q, but then when you get to 2, now it keeps increasing. So h is our true area function. And how can we write the area? So we can go from 1 to x of absolute value of P of t dt. Because it's the h function is truly the area function. We need to keep the function all positive. If we keep it positive all the time, we truly get area. Great class today, guys.